Okay, so let's speak about reductions and in specifically polynomial time reduction. So reduction is a transformation of a problem X into a problem Y, such that if we can solve problem Y, then we can solve problem X. And we are going to use reduction as a way to find algorithms, but also as a way to prove hardness. As we did with undecidability, here the hardness is going to be different. We are going to care about running time. So what is a reduction between languages? So we have a language LX and LY, and a reduction is an algorithm that takes an input and computes a new string W prime, such that the original string belongs to the language LX if and only if the computed string belongs to the language LY. And this is called Har-Peled reduction. It's a one-shot reduction. It's not the only kind of reductions there is, but it's good enough for our purposes. And this is the version when we speak about decision version instead of languages. It's exactly the same thing, right? We just want that if the computed string is in the new language, if and only if the original input is in the original language. Okay, so how do you solve a problem? Well, think about a reduction from problem X to problem Y, and we have an algorithm for problem Y. Then we get a problem for problem X, right? The algorithm does the following. It takes an input for X, it converts it into an input to Y using the reduction that we are given, R, which is just an algorithm, and then we run the algorithm on the computed string. We use the black box we are given for Y on the computed string, and this, as such, solves the original problem. Okay, I like to look at this as a black boxes. That's what I was taught in undergrad. So we have a black box for R. Well, I guess it's not a black box, it's more of a light yellow box, but you know what I mean. And it takes the input for X, it generates an input for Y, it feeds it into the black box for Y, and then it outputs yes or no accordingly. Okay, so that's the reduction. Okay, and for our purposes, the critical thing is that if the reduction is polynomial, then the algorithm, the whole new algorithm is polynomial. Now, this is of course not quite true, right? What we need here is two things, right? We need that the first black box and the reduction is polynomial time, and then the output it generates is of polynomial size in the original input. And then we feed it into the solver for Y, which also have to be polynomial. And since we are feeding a polynomial size input into a polynomial time algorithm, we get overall a polynomial time algorithm. So polynomial reduction preserves polynomiality if the solvers we have for problems are polynomial. And that's why we care about it, because being closed in polynomial time is what we want, because polynomial time for an algorithm is a good thing, right? It means the algorithm is solvable efficiently. Okay, now one way to think about this, you can reduce X to Y is as a relation, right? X is smaller or equal than Y. What do we mean by that? Well, if Y is easy to solve, by easy we mean you can solve polynomial time, and we have a polynomial time reduction, then X is easy to solve, right? And this also works in the other direction, right? If X is hard, then Y must also be hard. Because if X is hard but Y is easy and we have a polynomial time reduction, then we can solve X in polynomial time, which is a contradiction. Okay, so this is why we use this notation, X smaller or equal than Y, because we want to say this really captures hardness. Okay, and as you saw before, I used the subscript P to say polynomial time reduction. The reduction takes polynomial time, right? So So this is similar to the decidability and undecidability reduction we did, except that now we insist that the reduction would be in polynomial time, which requires much more care and makes things a bit less easy to do. Okay, this is it.